All right, everybody, let's get started. Sorry for the technical difficulties. We have one TV down, so that's kind of what's happening right now. Paying attention to me, or we pay attention to yourselves? One, two, three. I always give people grace one time. After that, you just get asked to leave. Okay? Good. No harm, no foul. So today, just really quick, I'm gonna jump back in to measures of dispersion real fast, just as a quick review. Because your chapter 1-3 online test is next week, and you also have an in-class, okay, empirical and percentile quiz. Okay, it'll be done on your computer with Respondus. Super, super simple, okay? Don't even worry about it, okay? Your calculator does like 90% of the work for you, just as long as you remember the buttons, okay? But it does bear remembering that we need to go back and kind of remember some things very, very quickly. So I'm gonna skip through this PowerPoint very fast, so that way we can get over here. And we talked about variance, I gave you that formula there. And we figured all that out there. Standard deviation, that's the guy, right? That's the guy we're gonna need to remember a lot, okay? Anybody remember what the symbol for standard deviation is? Is it Greek or can it be both? Both. So what kind of letter are you gonna see if it's population?
Sigma.
Sigma, what's kind of a telltale sign you're gonna be dealing with population? Greek, looking for Greek, okay? What's a telltale sign that you're gonna be dealing with, sample? Letters. Not all the time. I'll be giving you a letter today. Just kind of help you in the formula when you see the letters. Let's put it that way, because sometimes out here we'll still name stuff sometimes, okay? So notice I gave you that. So if you can find variance, take the square root, okay, and you've got standard deviation. But does your calculator give you variance?
No.
No. So to get variance, what are you gonna do? Square it, okay? So simple enough for that, right? So just be careful of the question, okay? Because sometimes it's gonna ask for variance, sometimes it's gonna ask for standard deviation. Just like I said, be careful. Remember with standard deviation down here, we see the n-1. Remember, that's just correction. Okay, that's all it stands for. Is it something you need to remember? Not really, because remember your calculator is going to give you two things. It's going to give you a sigma and it's going to give you for the population and it's going to give you the sample. You just need to know which one you need to look at the time. Population, look at the bottom, okay? So then we did this, we figured out how to get to there. And there's a perfect example right here. If you will notice, kind of right here, you will see this pull up the laser pointer here. You'll notice right here, we've got the population one. Okay, and then right above that, we've got the sample. We'll get into some of the other little portions today. You've also got, as a reminder, don't forget you have your mean. So your calculator in one function with just that list function, you've got three things it's working out for you. Your mean, your sample standard deviation, and your population standard deviation. So then remember, there was a so what moment. Who cares? What is the standard deviation? Well, I went through all this, and this is a coefficient of variation, but what you really need to remember, is remember that guy right there. Okay? This right here is right now, we're gonna call it a bell curve. Okay? It's also going to be turned into what we call a normal curve. You're also going to be called as a normal distribution or distributed normally. That's where we're headed to. But I'd like to go ahead and plant the seeds now. What is this symbol right there?
U.
U, which is it mean, median, or mode? Technically speaking, it's mean, but if you think about it, it's all of them, isn't it? Because do you see any skew happening? No, everything's all in one area. So there it is. So that kind of helps out a little bit, okay? It is normally distributed, okay, about the mean. That might be something you want to stock away for later. Something is normally distributed about the mean. Well, what is standard deviation? That's why we learned this, right? One standard deviation away from the mean. Okay, in either direction, positive or minus, okay? We can roughly say that 68% of our data will fall between one standard deviation. Okay? Can do that again. We can go to two standard deviations and realize that now we have how much? 95%. Okay? I want to remember this because this will be on your empirical and percentile quiz. I'll be asking you, fill this in. Okay? How much area is here? How much area is here? How much area is here? Okay? Is this normal? Would this be considered normal? If I said, hey, I was doing test scores and my guy here, his test score was in 2 standard deviations. Is that pretty normal? Yeah. Remember, within 2 standard deviations, that was what we can consider normal. Okay? Now, of course, we can have outside of that, anything beyond 2 standard deviations will be considered not normal, weird, irregular, however you want to describe that. It's something that's saying it doesn't happen very often. Doesn't mean it can't happen. As we get into closer to chapter 4, which we'll get into chapter 4 this week. Okay, notice, luckily, barring technical difficulties, we're still kind of ahead. Not by very much, but still we're a little bit ahead. We're going to get into probabilities. Anybody hear somebody say, man, there's 100% probability that this is going to happen, or there's a 0% probability this is going to happen. That's actually a lie. Okay. In statistics, nothing's ever truly 0%. Nothing's ever truly 100%, but it can be so close to 0 and so close to 100%, it might as well be one of those extremes. Does that kind of make sense? Okay. What would be a good example of, well, I'll just say how I use it. Okay, just so that way you know. I use standard deviations every single day. Okay? I have a little program that I wrote. I pull data from you guys. I plop it in my little sheet, and it starts popping out times, like say lesson 3-2. Okay? And it'll say, hey, out of all my students, okay, this is the mean. Because I want you to realize, am I dealing with population right now? I'm not doing statistics, I'm doing population. So it gives me your population. It says, this is the mean time it took these students to do this homework. Okay, so I've got a baseline. And then I start saying, okay, well, let's start looking. Who is within 2 standard deviations, which would be normal, right? I take those people, they get erased. Then I start looking at the people on the outsides. Okay, I've got the negative side, right? I've got the positive side. Now, you tell me, what am I looking at when I'm looking at the negative side? I'm looking at this side over here beyond 2 standard deviations of time. What do you think I'm thinking those students are doing? Cheating, why?
It's outside of the 2 standard deviations.
Well, so is over here.
They're taking this time, taking too long.
Those are taking too long, so maybe they're having trouble. These over here, I'm like, now, is it possible somebody just got it done that quick? Yes. But do you think it's raising some alarm bells? Yeah. It's gonna pique my interest. Like, okay, maybe lesson 3-2, I'm not gonna look at. But then I might go back and look, is this person showing up on 3-2, 3-1? Other homeworks, and they're consistently in that range. Well, then that person might be getting an email going, hey, you might want to take a little bit more time. And I'll literally say, I know what you're doing. Okay. But then on the flip side of that coin, if I see somebody consistently over here, what do I need to do? Probably reach out and go, hey, something going on, do you need some help? What you can also do, like with me, I always email Hawks and go, are they moving their cursor around? Because sometimes I know what you do. You just walk away and just leave the browser on for a while. So that can also cause a larger standard deviation. So I'll go with that. Now notice, so back, you need to know that 1 standard deviation away from the mean is 68%. 2, 95%. 3, 99.7. What would be the total area? 100. Remember, this right here, even though I didn't draw it that way, is asymptotic. Remember that from college algebra? It means it can never touch. It will never touch the x-axis. This is the x-axis right here. It will never touch it. This will shoot off to infinity, but it still has an area of 0.15. I get it. Something going off to infinity, but still having a finite area. That's calculus, just trust me. Okay? So notice we can also do this. You will need to know this as well. Good news, you only really got to know half of it. Right? Because if you can memorize this half, then what? You got the other half. It's a mirror image. It's symmetrical. Okay? So you got 0.15, 2.35, 13.5, and then 34, which makes sense because 34 and 34 make the 68. Okay? So notice if you figured out the 34, you can start doing the math and figuring everything else out from there. Okay? It may take a little bit of calculator work, but you can do it. Okay? Why do you need to know them like that? Well, because you can have that. As you can tell by one of your homework questions, if you've already started working on your homework, it says, hey, what is the probability of, or how much data is in this area less than something? And that's what it's saying, hey, less than. That means you gotta count everything, okay? Not just a bounded area in between something, but everything below it, okay? Sometimes everything above it. So this would be the empirical part of your empirical rule quiz, okay? The other thing you're gonna have to know how to do is figure out your standard deviation and stuff like that, but we're gonna work out that in the next lesson. So any questions over this? Any questions over what possibly might be on your quiz on this part of the quiz? Okay. And like I said, the empirical part is literally that. You might have one question saying, how much of this is less than something? Okay. But, and that it should be just fine. Then I think, yes. Now, I've showed you this Chebyshev's theorem. I want to write this down again for you. Let me see if I can actually probably write it on the screen today. We will see if it likes me today. So we got K is equal to X minus mu all over standard deviation. That is your Chebyshev's theorem. I want you to remember that theorem. Look at the K, look what it equals to. And see in a little bit if you really need to memorize that. Now remember, this is what Chebyshev's theorem says. That if I have a data point, I'm going to give you a mean, and I'm going to give you a standard deviation. When you do the math to this, good news. In this class, it's always going to be a pretty number. I promise you. Okay? But notice, if I end up getting a 2, that's how much data is in between. Okay? If you end up getting a 3, that's how much data. Okay? Those are the only two things you got to remember. That is for this theorem only. You will know when you need to use it because on the question on your midterm or even on your quiz, I tell you, using, okay, Chebyshev's theorem, tell me how much data, whatever, and so on and so forth, okay? So you won't have to wonder. I will be explicit in what I say. Are we good? Any questions? Entertain any question. Okay. So let's jump into 3.3 measures of relative position. Okay. If somebody's wondering, there is no rhyme or reason what pictures I chose for the background. I think it was whatever mood I was in that day. I think maybe this day I saw a cat and I was like, I'm gonna put a cat. And then just let people wonder why there's a cat there. Okay, measures of relative position. So let's think about What did we learn so far? We started 3-1 learning about center, right? Can't really measure anything if you have nowhere to start. Okay, so we learned about different measures of center. Mean, median, and mode. Okay, and to be honest, and we learned about what can affect those. Like, mean is really influenced by outliers. Okay, now we're going to be using mean a lot, but we're not going to be worried about outliers as much because remember that little distribution I just showed you? We're going to be using that type of distribution a lot. Okay, so mean, we're not going to be worried about outliers pulling us to and fro. Learn how to find mean. It's obviously on your list function. You can also add up all the data points. And then you also got a big N and a little n. That depends on what. Big N is always going to be population. Little n is always going to be sample. Perfect. We just went back through dispersion. Remember, that's where I talked about, like if you're pouring like liquid into like a water or heavily viscous liquid, I think I use like KY and then like wax. It just depends on like how heavy that stuff is, how far it's gonna like move away. But it is a dispersion, right? And then we just went back through that. So you got your empirical rule, which talks about the mean. Everything is measured from the mean, the population mean, the mu, that kind of backwards Y U looking thing. One standard deviation is what? 68%. 2,
95,
3.
99.9.
Very good. Anything beyond 2 is not normal, however you want to phrase that. And then anything inside that is going to be considered normal. Why does that matter? Well, let's think about it. I mean, as I get into this, when someone says on the news, this is within 2 standard deviations and they're trying to scare you, you can always just go, "That's normal." Right? But they're trying to compare something, you go, that's not even weird. Okay, that's how you can kind of think. But now we have measures of dispersion. So we're going to learn about percentiles first. Okay. Can anybody tell me, knowing that I'm going with 1 standard deviation? Okay, I'm not trying to trick you on this one. This is obviously the mean right here. Okay, and then this is obviously 1 standard deviation plus or minus, right? So I'll put that down. That mean right there. Well, how much data is colored in?
98.3.
Think about it. What's this point? How much data will be from right here back?
15.55. I don't know.
50%.
Stupid.
Half of it, right? How about the other point? Now we take 50 and we add how much?
84.
Hmm? Very good. So that's 84%. Everybody's doing good. Simple math, right? Well, if that's easy, how much is that? 75 now. But is that 25? Is that equal to 1 standard deviation? So the only reason you're able to say 75% right now is I was nice enough to give you the 25. What if I didn't give it to you? Then you're sitting there going, well, how far is that now? Okay, that kind of makes sense, what we're saying? Okay, we're gonna get into that. Now, this is what we call a percentile, okay? What a percentile does is says this. Okay, you have 75%. Anybody here taking their SATs and all that kind of stuff yet? Have you heard the word percentile yet? Okay, what have they said? You're in the 75th percentile. Or to get into this college, you need to be in the 80th percentile. Anybody have any idea what that actually means though, when the teachers start talking about percentiles? If you're in the 75th percentile, I mean, you're better than 75% of the people who took that test. Okay? That also means what? You're not as good as 25%. That's what that 75% means. That's where it puts you. It says, hey, this is where you scored, right here. So if you're looking to get into a college or a job or something like that, military, if the military says, hey, to get this job, you need to score this percentile on this exam. There you go. That means you need to be better than 75%. So when you hear somebody scoring like 99th percentile, you know they're better than 99%. You are being too loud. Does that make sense? Good. Kind of straightforward, isn't it? I mean, now that you kind of hear explained that way, hopefully it kind of makes a little bit more sense to it now. So even if you if you get your scores back, I mean, I don't know. I know when I got my scores back, it said you're in this percentile. I was not very high. Okay. So the car manufacturer, what is the percentile? The car manufacturer is studying the highway miles per gallon for a wide range of makes and models of vehicles. Hog's favorite mode of showing you things is stem and leaf plot. I don't know why I can't stand these kind of things, but still, whatever, we'll show it to you anyway. For a wide range of makes and models of vehicles, the stem and leaf plot below contains the average highway miles per gallon for each of the 111 different vehicles the manufacturer tested, which would be in the 10th percentile and which would be in the 15th percentile. So here's our stem and leaf plot. Okay. Remember to read a stem and leaf plot, always look at the key, okay? It's gonna give you a key right down here at the bottom. Look at it first, and it'll tell you, here's how you read me, okay? If you don't look at it, it's honestly really confusing because you could be reading it as 121. Well, that didn't make any sense, but notice even if we look at this first one right here, just kind of get out of the way. This right here is saying, hey, right here, that's 12.1 miles per gallon. The next one will be 13.3, 14.1. Now look at the 15.6, and then, 15.5, and then 15.6. It's got two data values there. They're just using the last numbers, the tenths places, okay? So here's how we're gonna do it. Anybody recognize this little symbol, what this means? Are you little college algebra students? Go back to basic math. How do you make a number a percent? There it is. Divided by, you're basically finding a percent. Okay? So notice, I'm gonna show you how to do the 10%. You do the 25%. So to do this, we're gonna do that right there. We're gonna take 111 and multiply it by 10 divided by 100. Do you need to do 10 divided by 100? Or can you realize that that's saying 10%. But if I was gonna put that in my calculator, what am I gonna put? 0.1. Okay, not one. One would be 100%. Remember, whenever we are turning things into a percent, okay, we multiply by 100. Okay. Or sorry, divide by 100. Good. All right, so if you do the math to that, you're gonna get 11.1. Here's the problem. There's no data value up there that says 11.1. Okay, so here, always round up. Okay, always. So notice we round up, we're gonna get 12. Well, what's 12? 17.1. Okay, well, how do I know that? I counted 12. When you start counting in here, notice I can come here and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And there it is, 17.1. Count the data on the left side. You don't count this side here. Remember, that's your main number. All the data values are on the other side, okay, of the line on a stem and leaf. Everybody understand why that 10% became 0.1? Okay, good. Unfortunately, I don't think your really fancy $100+ calculators have a percent key. kind of irony. Okay. Figure out real quick, I'll give you 1 minute. Figure out the 25th percentile. Okay, see if you can do it.
Is that formula, the L equals N times B over 100, is that going to be used for percentile everywhere, or is it just for this?
Percent for everywhere, for percentile, for right now. Yeah. Your calculator does it for me. Not this one, but the one I'm about to show you, it'll do it for you. Is asking if we're always gonna use this for percentile. For this type of question, yes, we'll always have to use this formula. We're gonna be using this formula a lot in chapter 4, because in chapter 4, we're getting into probabilities, which is why I wanted to take us a little bit ahead. Because probabilities get a little weird. It's probably one of the more abstract sections. Okay, what we're gonna start learning. So let's do the math of this very, very quickly, if you don't mind. I've got 111 here, always multiplying by the maximum amount of data. What am I multiplying by? 0.25? Right. 0.25. When you do that, what are you gonna get? 27.75, she's correct. She rounded up. And she got, oops.
No.
This is actually why I like my iPad better. I can just squeeze the tip and erase out. Here I have to kind of find all these things, okay? So now, well, we know the last one was at what? Was it 12? So let's just continue counting. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. What number would that be? Exactly, so that's 19.3. Perfect. Now, above everything else in this class, what I always want to kind of stress, what does that mean? Great, you found a number. Good job. But what does that mean? What is that 19.3 telling you? You're gonna go buy a car. And they say to you, well, the gas mileage on this car, man, it ranks at the 25th percentile. 10 minutes ago, would you have known what I had said to you if I was a car dealer? And now, what is he basically saying?
Better than 25%.
Yeah, but what's it worse than? 75%. That means there are 75% of the cars out there that get better gas mileage. Always ask the other question. Just because something's better than, always look at what's it worse than too, you know? It's like the thing, when I was talking about studies, and I said, hey, when looking at a study, when someone says, hey, there's 10 studies, scientific studies proving me right, then ask them, how many's proving you wrong? If 10 studies say I'm right, but 1,000 say I'm wrong, president. You know, it's like the old thing, one person calls you a donkey, don't worry about it. 2 people call you a donkey, you better start thinking about it. 3 people call you a donkey, it might be time to go get a saddle. Okay, so think of it that way. Good? Quartiles. Quartiles are this. Quartiles are values that divide an ordered array of data into 4 equal parts equivalent to the 25th, 50th, and 75th percentiles. This is part of your percentile quiz now. We are actually at the end of that. You have a Q1, first quartile, Q2, second quartile, and third quartile. Well, what is that? My excellent PowerPoint skills are just going to show you. Notice that the lower half is right there, right? Knowing that that says Q1, how much is in there? How much data should be in that area right there? 25. How about there?
50.
How about there?
75.
Yeah. You want an easier way to remember that? Look at this. Quartiles. Quarters. Remember it that way. One thing I want to add to this, okay, as we kind of do this, is look here. Whenever you have data, remember whenever you did range, you always have what? How'd you find range? You'd have two numbers.
Biggest and small bigs.
Exactly, biggest, smallest, minimum, maximum, wherever you want to say to remember. I'm gonna have a minimum. I'm gonna have a maximum. Okay, you've seen these. Whenever I get done drawing this, you're like, oh, I have seen these before. Okay. So you have a minimum data value, and between your minimum data value and your Q1, 25% of your data is gonna fit right there. Q2, what else, just looking at that, look at this guy right here. What else do you think you could call him? It's something we figured out. Think of our think of our centers, when we were doing measures of center. Let's say,
Median?
yeah. Median. So Q2 can also be called the median, okay? It's your middle number, dead middle, okay? Good so far? So here I have some data. Okay? I want you to get out your calculator. One, so you have the practice of this, and I want you to put everything into your calculator. You know how to get to your list function, right? Okay? I will remind you. Remember, you put stat. Then you go where? Huh? Edit, very good, edit. And then we're gonna start putting everything into our L1. Remember, always make sure if you're only putting things into your L1, your list one function, there's nothing in your list two, you don't want anything over there, obviously. It doesn't really matter since we're only gonna be calculating off our L1, but I always say, and better safe than sorry. When you do it, somebody give me the mean. I just want to see if you can kind of like, let's always remember, go back and do review when you can as you're learning something new. If you always go back and do some review, it's always going to be easy. Because let's think of this. The following speeds of motors in miles per hour were obtained by a highway patrol officer on duty one weekend. Determine the quartiles of each of the data set using the approximation method. If you want to learn the approximation method, it's in your book. Or how about we just use our calculator and not have to worry about doing extra math? How's that sound? Sounds a lot easier, right? But now I want to ask you questions as you're doing this. Would this be considered a sample or a population?
Sample.
Sample. Does it specifically say sample? No, it literally says the following speeds of motors in miles per hour were obtained by a highway patrol officer. So this is his what?
Population.
Population. Okay. So does somebody have a mean for me?
70.5.
Very good. Now, what type of standard deviation would I be looking for? Would I be looking at the sigma or the S on my calculator?
Sigma.
Sigma, exactly. So what's my sigma?
6.87.
Very good. So we could reasonably say that you have a mean here, right? And then, so if you went 6.87 plus or minus, how much of your data fits in between there? Very good. You see how we can just kind of review as we kind of go along? Well, let me show you what you should see on your calculator now. You got your calculators. That's what you should see in your calculator. And wow, remember when I told you need to find the Q1, median, Q2, and all that kind of stuff? Hey, look right here. Calculated all that for you. Okay, it gave you your minimum number. It gave you your maximum number. It gave you your Q1. Okay, it gave you your median, which would also be considered our what? Q2, exactly. Gave us our Q3 and it gave us our max. Kinda nice, huh? Calculator doing all that, you really only learned one button so far, okay? You ever need to do this on Excel? This is how you would do it, list all your data there. What's really nice is, like I said, why would you try to draw graphs nowadays? Man, Excel does everything for you. Notice Excel literally just said, hey, this is what you want, let me give it to you. And there it is. Very simple. Think about how long to create that graph, if you need to do it for another class at some point in time. It's 2 seconds, right? Good? Okay. If you have to draw one, okay, like possibly fill in one on a test, I don't know. Look at it this way, using that same data. I have my calculator, right? Come in here, there's all my information. I automatically put lines where my minimum and my maximum are. Then draw a straight line. Get rid of those. Now that's gonna be my what? What's that 65? Exactly, what's that one?
Your two.
Or
Oh, yeah.
either one, I'll take either one, but I want you to know both. Very good, Q3. Notice I just put a box there. Okay, fill that in there, clean it up, get rid of the lines, and there we go. Simple box plot. Okay, now I'll say box plot. They actually call these box and whisker plots. Now you know why I use the cat. Okay, because they look like little whiskers, okay, coming off. Now, nowadays, what we actually see, turn them on their side. And you'll sometimes hear those called candlesticks, okay? You'll see those a lot in financial markets. Like if the box is heavier at the bottom, that means more things have been sold. If things are sold at the top, things will be pulled up in this direction, okay? So if you get into finances, you'll see it a little bit more, okay? But notice if you had to fill in all this information, how much of my information sits between my minimum and my Q1? How much of my data should be right here? Exactly, 25%. That's why it's called a percentile. It's quarters, okay? How much of my data sits inside here? Exactly, and then right here. Exactly, so we got 25%. 50% and then 25%, exactly. Because it has to equal up to what? 100%. If it doesn't equal to 100%, you didn't include some data somewhere. Okay, so exactly. Just remember your quarter. That's how I always remembered it. I remember quarters at it's got 4 points, quarters in each one, okay? We good on that? All right, standard scores or Z scores, okay. Something that you're going to have to know, okay? Like, say it to yourself before you go to bed at night. Because this is something that's gonna be around the rest of the class, okay? At times, your calculator will do it for you, at other times it won't, okay? It depends on what we're measuring, okay? So what is a Z-score? It's a statistical measurement that quantifies the distance between a data point and the mean set of data. What does that really mean? It gives you the exact standard deviation. Okay? Because in the real world, okay, picking on him again, do you think he's going to be exactly 1 standard deviation away from the mean? No, the world doesn't work that way. When I start calculating him, he's going to be 1 point something else away from the mean, or maybe in the other direction. So things get a little bit different. They're not exactly perfect, okay? Showed you this one. What we're seeing here is this. This is why we need a Z-score, because right now you could say my data is how far away from the mean. Pretty standard deviation. Really easy to see, right? It's right over here. Okay, kind of see it? Let's get out of it. Right here, right? Can see that. Well, notice though, now where's it at? I didn't give you any information, you know, I didn't give you the 25% that you were hoping for last time. I just said, hey, how far? We know it's a distance, right? Like there is a distance right here. But we don't know exactly what it is. And that's what a z-score is going to tell us. Okay? So conceptually, what is a z-score? Exact measurement of what? Exactly. From the mean to the data point. It's the best way, it's a great way to say it. From the mean to the data point. Can you have a negative z-score? Can't? Don't forget the other side. Yeah, you can have negative. Okay? That's all we need is z-score. There's your formula. Good news, they're pretty much the same, okay? But you do need to be careful, okay? Just remember, we're looking at some Greek letters and we're looking at some, inside the formula, we're looking at some variables, okay? Variables, normal numbers, sample, Greek, population. Mainly right now, we're going to be dealing with population, okay? We'll sample in right now because you're learning about z-scores. We'll sample in some samples, okay? Good news is, bless you, good news is remember, if you go back to whenever I was teaching you about average or arithmetic mean, sorry. Remember how basically they were both the same formula? It should just one used the big N, one used the little n, but you can still get the same number. It's sort of that way with z-scores. Good. It's pretty straightforward on that one. Just kind of know what the formula does. So let's dissect it. So what we have here is this. We have z is equal to x minus mu all over the standard deviation. Remember, that right there is your what? Population standard deviation. This right here, population mean. This right here is what?
Yeah.
Exactly. That's a piece of data, okay? And that's why I wanted to write that. That right there is like some piece of data that was given to you, okay? Think back to the highway patrol one. You could go in there and pick a number off that and go, okay. Let's say one of the numbers was 72. I don't exactly remember the numbers off the top of my head. You go in there, you plug the 72 in, you've already found your mean, you know your standard deviation. You can say, oh, okay, 72, that's within this many standard deviations, okay? Is this piece of data normal or is this piece of data kind of weird? Notice it can kind of tell you that, okay? If you just get handed just a piece of data, not a whole bunch of data. So you can tell a lot about something if you have a mean and a standard deviation of something. Okay, I had a friend do, well, not a friend, a guy I know, he did a study over Dollar Generals. And their prices, because he said, man, everybody's going to these Dollar Generals are popping up everywhere because it's good for the economy in those areas. It's actually a lie. He did the math to it, found the standard deviation of it, found out the ounces of things. And he goes, it's actually more expensive to shop at Dollar General than it is to shop at Walmart. He goes, because of how much they're charging per ounce per stuff. And he started finding out that the price of those things were outside the standard deviation and stuff. He's like, man, he goes, never would have thought that. So notice, yeah, that got a little nerdy, but I was like, that's pretty cool. You know, that he found that out. So needless to say, we don't do a lot of shopping. If we're trying to save money at Dollar General, places like that. Okay. Good. What's an example? Jody scored an 87 on her calculus test and was bragging to her best friend about how well she had done. And yes, calculus students do that. But she said that her class had a mean of 80 with a standard deviation of 5. Therefore, she had done better than the class average. Her best friend Ashley was disappointed. She had only scored 82 on her calculus test. The mean for her class was 73 with a standard deviation of 6. Who really did better on her test compared to the rest of the class, Jody or Ashley? Okay, notice we're gonna be using a z-score, okay? Because now I can't figure out, you could go in there and start trying to do the math, you're not gonna get a perfect little like area of where they're at. So we come in here and we have a z-score. So let's write down, we got z is equal. Let me make this, I'm gonna hit this in a little bit. Z is equal to, can anybody remember our formula?
X minus.
Very good,
Mu
very good,
over population.
very good. All right, so that's gonna be the formula I'm gonna use, and I'm gonna have to do it twice. I've gotta do it for two different people. I've gotta do it for Jody. Okay, and I'm gonna do it for Ashley. Well, knowing our formula here, a data point that is given to me for Jody is going to be the 87. What is the mean of her class? Very good, 80. What is her standard deviation there? 5. Go ahead and fill in the information. How about for Ashley? What was she?
82.
Very good, 82, with a class average of and a standard deviation of 6. Give me some numbers.
1.4, 1.5.
For who?
Jody, Ashley's 1.5.
Ashley's what?
1.5.
So who actually did better? This is where you need to start learning today, and I've said this before. Start drawing. Okay? It doesn't have to be perfect. I am not looking for artists. Okay? If it's hard to conceptualize, draw yourself a little easy normal curve. We know we have what? A mean right here, right? Notice it's basing everything off what? 1 standard deviation, 2 standard deviation, 3 standard deviation. We know it's in the positive direction. So I can say this right here, 1 standard deviation. So can we all agree that say Jody's probably, if we went to say 2 is here, Jody's gonna be right about here. I'll put it in. Where do you think Ashley would be?
A little bit further.
It's a little bit further along, right? We'll put it right here just so you can kind of see the difference. Okay, so there is an A. So looking at that, who is better?
Ashley,
Why?
because she's further away from the mean.
Further away. Go back to your percentiles. Remember what it's saying. If you look at that as a percentile, it's saying Ashley, compared to everyone else, you can figure out a percent on that. Okay, you don't need to. You can say she's better than this many people in her class. This many people did better in her class. Now remember, she's comparing her class. Okay. Jody did a little bit less. So yeah, comparatively speaking, yes, Ashley did better. Not by much, but still, Ashley can therefore be very proud of her score comparative to her class now. Are we good? Does that make more sense? Forget the math behind it for a little bit. Does that make sense what you're learning right now? Okay. If it makes sense, it makes things a lot easier to read, especially later on. Okay. So let's do some examples here. Try to work that out and then I'll play catch up. Okay, we're going to consider a data set in which the sample mean is 99 and the sample standard deviation is 6.9. Calculate the z-score given that x is equal to 94.9. while you're working, I realize what's happening with this sample Z-score. All of you would be my population. I could find out a mean and I could find out a standard deviation from them. Okay? Now, and I could also pick out pieces of data, whatever I'm studying. Now, if I took a sample of, say, 8 of you, could you all agree that I could take now out of that sample, I could come in here and go, okay, let me calculate a mean. Let me calculate a standard deviation, and then let me pick some data out of that. That's what's happening here, okay? Because let's be honest, we're doing a lot of things with population. Does anybody ask the question of why are we doing lots of population yet? This is a statistics class. If we knew the population, would we need statistics? No, you know everything, okay? I don't do statistics when I'm studying every single one of you. I do statistics when I study a small portion of you, okay? So kind of keep that in mind as we go through this. Notice we're gonna be using a Z-score again. Okay, so here we are. We've got a Z is equal to, well, we're gonna still have a data value, right? I'll go ahead and give you that one. X minus what? A mean?
X bar.
X bar. Because what is the operative thing that tells me I'm gonna be dealing with an X bar? Yeah, got a sample happening here, okay? And so instead of this being divided by sigma, we're gonna divide it by what? S. Okay. So once again, they give us some data point here. We got 94.9 minus what? 9, all divided by 6.9. Anybody got a number for me? 8.59, or round it up to
0.60.
negative 0.60. And annoyingly, Hawks is going to want that 0, okay? So just kind of, because it does tell you, hey, round to 2 decimal places, okay? Even if that decimal turns into a 0. So notice it said round to 2, you got 0.59. You gotta look at the next one, so it's probably 0.59 and greater than 5. You had to round up. And then, there you go. Good? Okay. A manufacturer makes bags of popcorn and bags of potato chips. This is possibly a midterm question. Okay? The average weight of a bag of popcorn is supposed to be, okay, 3.06 ounces with an allowable deviation of 0.3 ounces. The average weight of a bag of potato chips is supposed to be 5.05 ounces with an allowable deviation of 0.1 ounces. Okay? A factory worker randomly selects a bag of popcorn from an assembly line, and it has a weight of 3.08 ounces. The worker randomly selects a bag of potato chips from the assembly line, and it has a weight of 5.04 ounces. Which description closely matches the findings on the assembly line? More than anything else, especially in this class, what helps out a lot is to tell yourself a story. What is it actually telling me? Okay, because some of this, especially when we get to probability, can get a little bit murky. Okay, we've all gone and bought popcorn. We've all gone and bought bags of potato chips. Okay, and we always kind of go, man, this thing's got a lot of air in it. I don't know, but there is a certain amount of weight. Now, it can't be an exact weight because let's think about it. Not every single piece of popcorn is going to weigh the same. Not every single potato chip is going to weigh exactly the same, and they're not going to start breaking off chips and just putting dust in there until it equals a certain weight. That allowable deviation, okay, that's that plus or minus. Okay, that's how come we have deviation. You'll also hear the word variance. A lot of these actually use variance, these factory top setting questions. Let's think about it. Remember, variance is the variability. Okay, so we need to see now, here's what happens. This thing's just pumping out chips and popcorn all day long. And then there's a worker that's got to go through there every once in a while and grab a bag. Okay? Why is he doing that? He's hungry? What's his job? Yeah, he's going to check. He's like, hey, you know what? What if the machine is not working right? What if it's not calibrated right? Okay, first off, we don't want to be giving people too little chips. We're gonna get in trouble, we're gonna lose money, probably get sued. But we also don't want to give them too much because, once again, we're not gonna get sued, but we don't want to lose money. Okay, because our profit margin is based on this variance. Unfortunately, these numbers are not perfect standard deviations. Hence, what's our ace in the hole? The z-score. Okay, so we see what the z-score is on them. So the very first one I'm gonna look at is I'm gonna look at the popcorn. Can anybody tell me if I'm gonna be using a sample or am I gonna be using a population? Sample, because he goes in samples the assembly line. So that is gonna be our x minus x bars. I'm just gonna do that, I don't wanna waste my time. All over the sample. So for the popcorn, we have an x minus x bar. Notice our data point, the thing he pulls off the assembly line is the 3.08. We're gonna minus that from what? 3.06. And divide that by 0.03. Do the same thing again. Okay? Gotta do the same thing for the what? Potato chips. I'll put chips. Chips what? He's gonna pull something off, and he pulls something off. The data point is gonna be 5.04 with a mean of 5.05. All divided by what? 0.01. Should probably be using my approximation one, but I'm not worried about that right now. You do the math correctly, you should be getting 0.67 here, and over here I've got -1. Okay, that's all fine and dandy, but notice it wants you to say, what does this mean? Okay, well, you need to start going through here and go, okay. The popcorn bag assembly line is closer to the specifications given because its z-score is closer to the standard than the potato chip assembly bag. Does that sound good? It's saying, is this number closer to the mean than this number? Do you think it is? What number's smaller? Would you rather have $1 or 67 cents? Think about it. That's what you're seeing when you're seeing that fraction or that decimal right there. So which one is closer? Okay. So that's a possibility. That makes sense at least, right? So that is a possibility in there. Let's kind of keep this guy in mind. Remember, like any good test taking strategy, you kind of want to just go through which ones seem logical, which ones are just like, that's stupid, that can't be an answer. Okay, the popcorn bag assembly line is closer to the specifications given because its z-score is further away from the standard. Does that make sense? At all? No, that doesn't work at all. So that goes against our definition. The potato chip bag assembly line is closer to specifications given because its z-score is closer. Does that make sense there? Is this number, the -1, closer to the mean than the 0.67? No, that doesn't work either. And then here, this last one, the potato chip bag assembly line is closer to specifications given because its z-score is further. Remember what the question said. The guy's gonna go grab a bag, right? And those specifications have to be where? Within this area, right? They can't go outside of it. So do we want something that's further? Does that kind of help you kind of see what it's saying now? So no, that one does not work either. So the only one that makes sense is this one right there. The popcorn bag assembly line is closer to the specifications given because its z-score is closer. It's fitting within that variance. It's fitting within the standard deviation they have set. Okay. Then compared to the potato chip assembly line. Go through there and talk to yourself. Imagine you doing what they're doing. I'm going in here to pick out a bag of potato chips. Okay, and it needs to fit. Okay. Let's do one more. Easy breezy one. A high school has 36 players on the football team. The summary of the players' weights is given in the box plot. Approximately, what is the percentage of players weighing less than or equal to, or just so you know, that symbol there, okay, to 225 pounds? Let's remember, a box and whisker plot says this. This right here, let's do a quick review. What is that number there? Minimum, exactly. What is this number there?
Or Q1.
Q1. What's this guy here?
Or Q2.
Exactly, median or Q2. What's this guy right here? And what's this guy over here? Max. How much information sits between my minimum and my Q1? Exactly, 25%. How about between Q1 and median? Exactly, we've got another 25. It's kind of straightforward, right? And then what? I got another 25 here. And then I got a final 25. How much information sits inside that box?
Inside the box itself.
Inside the box,
50.
50%. That's why we kind of like it, so we can say, hey, I know that box has 50%. And here's the data values, they're inside that 50%. So most of my data fits where? In a box plot. Where is most of my data? Between what? Q1 and Q3, right? That's where 50% of my data is, okay? So, how much? How many of the players weigh 225 or below? Exactly, 75%. Let me tell you what's coming, so that way you don't walk in here next week all like, I didn't know. Okay? Tuesday, we will be having our empirical rule and percentile quiz in class. It will be happening on your computer. You can also do it online. Everything will be on the computer. It has a 30-minute time limit. Okay, it's a very straightforward, easy test, okay? As long as you've done your homework and studied this a little bit, okay? Chapter 3 homework is due on Sunday, okay? We will start 4-1, okay, on the next class. We're gonna be starting probabilities now. Okay, a lot of your probabilities, unfortunately, your calculator does not do for you. Okay, so it's gonna be a section of class that there's not a whole lot of calculator work that's gonna be done. It's gonna be all you. Okay, having said that, just kind of want y'all to be aware of all that that's coming up. Okay, so if you're having any trouble right now, okay, you need to get with me, email me. Also, if you're behind, get caught up. Okay, we're getting to that point of like, it's not gonna get harder, but it is gonna get more abstract. Probabilities are harder than you think, okay, because just in the way they word things, it's gonna be the way they word problems, okay? And it is about 2 or 3 questions on your midterm, okay, the probability problems. Because believe it or not, that normal curve you're looking at, okay, it deals with probabilities. Okay, everything deals with probabilities, okay, so we'll get into that, we'll walk slowly, okay? And then just to kind of keep you the heads up, remember, I know this class is a Tuesday class, but don't forget, not next Monday, but the Monday after that, there's no school. Okay, it's President's Day, and so there won't be any school, the campus will be closed. Okay, so if you do have classes on Mondays, on the 17th, we will not be open. Okay, so you have a great day, I will see y'all later.